Allumage moteur Vulcain. Allumage confirmé.
Allo.
Doczuvane.
Salut. Servus.
Pronto?
여보세요? Eus. Alô? Hola. Guro.
Sawadee.
Bonjour.
Arigato.
Welcome to the Exploratorium. I'm Paul Doherty, Senior Staff Scientist at the Exploratorium and a planetary physicist. And today I'm going to give a program on what are comets. And I'm doing this because the Rosetta mission from the European Space Agency is about to go land on a comet. So here's a picture of the Rosetta spacecraft. It has these huge solar-powered sails, and it's now halfway between Mars and Jupiter and closing in on Comet 67P. Now, this comet actually has a name. It's Churyumov-Gerasimenko, but I'm going to call it 67P just for short. Now, the spacecraft was so far from the sunlight was so weak that even those large solar wings could not have enough power to power the spacecraft. So they had to wait for the spacecraft to come back closer to the sun. And just a few months ago, they turned it on again, and it came back to life. And just the other day, they opened the eyes of the camera, and they took this picture. And inside that box, there's a 1 pixel bright light. And that 1 pixel size light in that box is the first picture from the spacecraft of Comet 67P. Now, here's a picture of the comet from Earth. It definitely is a comet. Comets are named for coma, which is Greek for hair. Comets look like fuzzy stars. They've got blurriness around them. So here's the comet viewed from Earth. It's still just a bright point of light. It's actually a body that's about 4 kilometers, about 2.5 miles across. Dirty snowball, if you will. I'll show you some better pictures soon. And we're going to go there. And here is the movie showing you the Rosetta spacecraft. Look, in the distance are very out-of-scale images of the sun and the planets. And it turns out one of those planets you can see on the way to the sun is Mars, so we're outside of Mars. And Rosetta and the comet are falling together. They've now reached about the same orbit. And on the side box there is our prediction of what it will look like in August when we arrive at the comet. We're really close to the comet now, and they're falling together towards the sun, but they'll really reach the same point in space this August. So we've known about comets for a long time. Anybody that looks up at the sky long enough, and our ancestors spent a lot of time looking at the sky. They didn't have television. And so they saw comets and they tried to figure out what they were. And on the left here, there's a picture of the Bayeux Tapestry. In 1066, there was a disaster in England, and they looked up at the sky and they saw this star with a tail. Excuse me. And that was a comet. And they thought maybe the comets could foretell the future, and they usually foretold bad things. And then, with time, we kept looking at comets. The picture on the right is an actual photograph of a comet from 1882. And comets, big comets like this, have names. This one's named the Great Comet of 1882. So it's easy for me to remember when it came by. Here's a nice comet. This one is Comet McNaught in 2007. Now that was taken from Australia shortly after sunset, and I would have loved to have seen that comet. That's just a gorgeous picture in the night sky. Spans a distance bigger than your hand in the sky. Thank you. Excuse me. Great. Okay, so it spans a distance bigger than your hand in the sky, and it hangs there night after night, brightening up as it gets near the sun, because the sun is hot, and it's heating that comet, and the comet is outgassing, and I'll show you a model of that soon. But one thing, as you look at comets, every once in a while, they'll have 2 tails, unlike a cat. Now, it's often said that comets are like cats. They have a tail, and they do what they want. It's hard to predict how bright a comet will get as it comes into the sun. So we're not sure just how bright Comet 67P will get. But if you look closely at a comet, they often have 2 tails. And one of the things that a comet is a ball of ice in the vacuum of space with dust and rock around it. And as it heats up, that ice doesn't just melt, it turns into gas, it sublimes, and that gas expands and it drives the dust out into space. So one of those tails is a white tail of dust scattering sunlight. And it goes out, and the sunlight pushes that tail away from the comet, but those dust particles are in orbit. And being in orbit, they sort of curve off around. So that dust tail is a curving tail, like you saw in Comet McNaught. The other tail is a gas tail. And gases are really tiny atoms and molecules. And the sunlight can push them straight away from the sun. So you'll see in this comet here, it has two tails, a dust tail that curves and is white, and a gas tail that goes straight and is blue. Excuse me. Okay, so here's something you can do at home. So if I can have a little close-up camera, I'll show you a slightly dangerous at-home activity. We have this as an exhibit at the Exploratorium. So what I'm going to do is I'm going to take a material which on Earth is a solid. It's called dry ice. And that solid turns into a gas at room temperature. So I've got a few chunks of dry ice right here. You notice I didn't touch the dry ice with my fingers, because if you touch it, I just touched it. If you touch it for more than a few seconds, you can get second-degree frostbite. Well, I'm about to whack it with a hammer to make it smaller. Because I want pieces, whack it harder. I want pieces that are small compared to my fingernail. So I'm going to scoop up a few small pieces here, and I'm going to put them into the water right here. And really some interesting things you'll see, especially if we can switch to the video cam here. And there's some great things to learn by just putting dry ice on water. So here are these little dry ice particles. And the interesting thing is, if you watch them here, they are dry ice. Comets, in particular, have dry ice, carbon dioxide ice, inside the comet. And as the dry ice warms up, as it's doing here, the water is warming the dry ice, it outgasses, it sends out gas. Now, that gas, as it comes out, acts like a rocket motor, and it's causing a spin. You can see the collection of the dry ice particles is spinning right there. And get some more. In this case, it's on water, and there's water vapor around, and the coldness of the dry ice is making the water vapor condense into droplets, and so you see this mist surrounding the floating dry ice particles. And that mist is showing you the tail spewing out from our comet model, just like the tail spews out of a comet, except in a comet, that tail, as you remember, is dust being blasted out by the subliming dry ice, whereas here, the tail, as you see, is actually water vapor being condensed. So it's a little bit of a funny model. But there's something really interesting. You'll notice that whenever these particles come together, when they get near each other, they seem to attract each other. I'll get these two close together here. When they get close together, maybe that's not quite close enough. A little bit closer. There we go. They attract. And that's very interesting for the history of the solar system. It turns out that if you have rocks or dust particles in space, in the vacuum of space, they can come together gently attracting by gravity or maybe just randomly moving together. And those rocks in space, when they come together, can stick in a gentle congregation, just as these little bits of dry ice stick together here. If another particle comes in at high speed, it can blast them apart again. But sometimes they stick and grow into larger and larger collections of debris. And we think that's how the solar system is made. Those collections of debris gradually accumulate, making planets. And that's really interesting, because the debris, only solids can stick together. You can't have gases stick together until you have a solid to hold in the gas by gravity. Now, near the sun, it's hot. And near the sun, water ice is a gas. It's so hot near the sun that water ice cannot exist. It sublimes, it goes away. So you don't expect to find water ice near the sun. But out beyond the orbit of Jupiter, it's colder, and water ice can stick together. So if you find a collection of material around the sun that has water ice in it, you expect that it was made beyond the sun, beyond Jupiter's orbit around the sun. And if it's rocky or iron-like, you expect it's made inside of Jupiter's orbit. So Mercury is very much rich in iron, which takes very high temperatures to turn into a gas. And that's why we think that Mercury agglomerated close to the sun as an iron-based planet. The Earth's a little further away. At our distance, silicate, rock, does not vaporize. And so our Earth is made of rock. But out beyond Jupiter, we can have the ices gather and make comets. So we expect that comets are actually made out beyond Jupiter. Excuse me. Okay, in between Mars and Jupiter, there are rocks known as asteroids. And they didn't come together. Those asteroids, they're all smaller than the Earth's moon by a lot. Those asteroids never gathered enough mass to pull together to make a planet. It's like they're a planet that never happened. There just was not enough material to make a planet out there. Or maybe a planet was formed and it got blasted apart in a giant impact. We don't know if it didn't get together or if it got blasted apart. Asteroids were thought, we think of them not as comets. Comets have tails. The ices in the comet turn into a gas and make a tail. An asteroid, if you look at it, it doesn't have a tail. Or so we thought until we got this picture a couple months ago. The Hubble telescope, looking out at the asteroids, found this asteroid, and it doesn't have one tail, it has 7 tails. And that just is the kind of thing you discover when you have a new tool like the Hubble telescope, and you look at things and you realize, wait a minute, we always thought that all asteroids would be tail-free, and yet here we look at them, we've looked at 1,000 asteroids, we find one, it's got multiple tails. This is a mystery. We don't know about this asteroid and why it has tails. It must somehow have gases, ices inside of it that somehow got warmed up, and they're sending out the gas into space, driving the dust out with it. This is a puzzle in progress. And it's so neat that we have these continuing puzzles when we look out in space and ask questions. Well, we've been studying comets. Another thing about comets compared to asteroids are in a circular orbit, pretty much always between Mars and Jupiter. It's called the asteroid belt. Comets exist way out beyond Neptune. They're far out, and out there they're in circular orbits. But every once in a while, 2 cometary bodies will come close together, and the gravity of one will spin the other one in towards the sun. In fact, the comets that are far out can be 1/4 of the way to the next star. 1 light year away, they can be out there. And so even a passing star can jar that comet and send it in towards the sun. So there they start out, a light year away, fall into the sun in an elliptical orbit. So asteroids go around the sun in a circle, pretty much, ellipses, much like planets. Comets come falling in, zip around the sun and head out. And this diagram at the bottom is Isaac Newton's diagram. This one is actually made by Isaac Newton, plotting the path of the great comet of his time. And he actually, so there's an artist illustration of what the comet looked like in the sky. It was really important to the people at the time. And Isaac Newton just had figured out how gravity makes objects move around the sun. And he tested his theory of gravity by plotting the path of this comet, and he showed that indeed it followed the laws of gravity that he had just come up with. So this comet was a great test, and it showed us that Isaac Newton's laws were important. Well, since those days, we've actually gone to comets, and we're going again soon. So this is one of the most famous comets around. This is Halley's Comet. And the last time that Halley came around, we sent a spacecraft right by it, the Giotto spacecraft. And look at this thing. What you're seeing there is a nucleus of a comet, this ball of rock and ice near the sun. And that ball of rock and ice, the ices are evaporating, sending out the dust into a giant cloud around the comet. And we flew through that cloud, and the good thing was, as the spacecraft went through the cloud, it was not destroyed by hitting the rocks and dust, because it's coming through at high speed. It's like driving through a dust storm in a car. Your windshield's gonna get pitted for sure. And you can even see the spray of particles coming out of that nucleus. So this is one of our first good pictures of a comet. And then we went back and took a picture of Comet Hartley 2 in the epoxy spacecraft. And look at the tail end of that comet. You can see the dust shooting out like geysers as this comet warms in the sun. And one of the things we discovered by flying past this comet and looking at it was that it had dry ice, just like I showed you here. The dry ice warmed up and it drove out water ice. And the spacecraft picked up the signature of water ice. And so that was a great discovery from that one. And then, having discovered that, we decided we'd fly out there and bring back parts of a comet to Earth. So this is the comet Wild 2, which looks like Wild 2, but it's pronounced Wild. And the Stardust mission went there in 2004. Now the Stardust mission has this giant tennis racket sticking up from it. And that tennis racket had like a catcher's mitt. And it's a catcher's mitt made from something that's like fluffy glass. It's aerogel. And they flew through the cloud of that comet with this catcher's mitt and swept through the dust, and the dust embedded itself in the catcher's mitt. And then they folded the catcher's mitt back into the spacecraft, fired the rocket engines, and on the bottom right of this picture, you see the spacecraft arrived on the deserts of Utah. It was the fastest returning spacecraft we've ever had. It plummeted into the Earth's atmosphere, crashed into the desert. We opened it up. We looked inside of it. We found the dust particles from that comet Wild 2. And those dust particles, as I said on the bottom here, completely revised our view of comets. They found some dust particles that were crystals of igneous rock. They were pyroxene. They're rock crystals. And in our model of comets, we expected they'd formed way out away from the sun. And any rock or dust would come from the interstellar medium that would have dust grains from other stars around in that comet. What we found were rock grains produced near our sun. And here's another puzzle we don't understand. How did those rock grains that were made in the high temperature environment near the sun get out there to where comets form? We don't know. And so, again, we go out thinking we know the answers. We do the experiments. We find out we have more to discover. We also discovered an amino acid on the material collected from the comet and returned to Earth. We found glycine. And the glycine was a slightly different, there are two forms of glycine, a right-handed form and a left-handed form. And glycine made on Earth has only one form. And glycine made in space has both forms. And so we looked at this glycine and it had both forms, so we knew it wasn't earthbound contamination. We knew that this was an amino acid from space, and that's a really important discovery. It's a really important discovery because these comets made out there far from the sun, in this picture, the tiny little colors at the center are the sun and the planets we know and love. You can see Saturn and Jupiter. They're a long way from Earth, but all the green dots in here are comets beyond the orbit of Neptune. Comets start a long way out. This is called the Kuiper Belt of comets. And recently they discovered an even bigger secondary belt of comets. It's called the Oort cloud. And the little blue thing in the middle is that giant cloud of comets I showed you in the last picture. This cloud of comets, billions of comets, stretches a quarter of the way to the next star. And these fall in towards the sun all the time and bring in their material. Well, we want to know what's in the comets, so we actually, what do people do when they want to know what's in something? They explode something on it. So here's a picture of Comet Tempel 1, and that picture was taken from a spacecraft that was headed very rapidly towards a collision. That's the last image before it collided with the spacecraft, with the comet. You can see craters and dust. You can't see the ices, they're below the surface. And the right-hand picture, there was a second spacecraft following it in. So you had the spacecraft doing the collision and the cameraman. And here is the result of the explosion. It drove particles from inside the comet out into space, which we then examined. So it's like probing deep inside the comet. And that collision made a hole in the comet as big as a football field. And it excavated the insides of the comet. So that was a fun thing to do. Now here's the deal. When you go out and look at meteor showers, here's a drawing of a meteor shower from 1880. When you go out and you see those streaks through the sky, those streaks coming in are mostly pieces of comets. Each meteor shower is related to the dust from a comet raining down on the Earth. And in fact, comets strike planets all the time. Here's a picture of a comet striking Jupiter. Jupiter has this unblemished, wonderful surface, and those pockmarks, like zits, are giant comet impacts on Jupiter. Comets have impacted planets for the whole history of the solar system. That means, since comets have amino acids, and comets have ices, including water ice, and they've come to the Earth, how much of the amino acids that created or were the elements of life on Earth came from comets? We don't know right now. And how did it turn out that the two symmetries of the molecules that came from comets evolved into one symmetry on Earth? Great questions. Science doesn't know everything. We're still doing work to understand it. And to do that work, we're about to land on a comet, the Rosetta mission. And here's a picture. The line here is the orbit around the comet P67, Churyumov-Gerasimenko, and it's starting to drop into its orbit right now. And over the next few months until August, it's going to approach closer and closer, orbiting the comet. And then in August, we're going to land one part of the spacecraft on the comet. November, the actual landing will occur. Now, the orbiting spacecraft and the lander will stay on the comet as it falls in towards the sun. Right now, it's beyond Mars. It'll come in closer than Mars, closer than Earth, closer and closer to the sun, heating up, turning on as a comet. We're going to have our cameraman and our experiments with it as it falls, And we're going to learn the answers, hopefully, to some of these questions. What amino acids are there in there? What are the nature of the grains of ice and dust and rock in this comet? And then, of course, in the results, we'll get more questions that we thought we knew the answer to, but we really didn't. So science progresses by asking questions, trying to answer them, and discovering new questions we didn't even know about. So I'd like to, the audience here can stay behind and ask questions. I'd like to thank our webcast audience for joining us in the webcast studio at the Exploratorium for the presentation, What is Comets? Okay, so who has a question about Anyone have things